So my name is Diachin. I'm from Lawrence Livermore National Laboratory. I've been the director of this program since November, so less than a year. So this program has really been designed to really bring the power of high-performance computing to manufacturing. So we heard a number of great talks this morning about how impactful high-performance computing can be in the industrial sector. And this particular program is focused on accelerating innovation, lowering energy costs, reducing waste, optimizing process design, and it's trying to do that particularly in manufacturing. It's funded by the Advanced Manufacturing Office by the Department of Energy, and it's really focused on two primary goals. One is looking at reducing energy costs in the manufacturing process, and the second is the development and productization of new clean energy technology. So those are the two primary focus areas for the program. So when this program first started, there was a pilot project that we ran at Lawrence Livermore National Lab back in 2011 that was focused on, we called it HPC for Energy at the time, and it was focused on trying to understand how can we bring high-performance computing to industrial sectors. We took some internal funds, laboratory research and development funds, and directed them at 6 different projects that we called pilot projects that were small, very focused efforts to bring high-performance computing to different kinds of industry, including electric grid companies, a well boring company, et cetera. And from that, we learned a lot of lessons. There's a lot of research and work that's been done to understand, what's the status of the industry. There are a lot of large companies that use high-performance computing, some extremely successfully, but may struggle to some extent to keep up with the latest research developments in software. We heard a lot about how software is a major barrier for companies this morning. And there are very few small to medium-sized companies that are really taking advantage of high-performance computing. So that's what we wanted to address on the industry side. On the DOE side, of course, we've got many very large-scale systems. We've got a lot of expertise in how to use those systems. But one of the complaints I've heard at forums like this over many, many years was that the DOE lab system is somewhat opaque. And so it is very, very difficult for an industrial partner to go in and understand, what are the resources that are available? What are the expertise that's available to me? There's 17 different national lab systems. We all have our own websites. It's not easy to navigate for a company. And so the idea was to reduce those barriers, to bring the expertise that exists at the Department of Energy laboratories to the industrial sector. And so that's what this program is trying to do. We're trying to build that ecosystem, that community of using high-performance computing in the manufacturing sector. We're doing this primarily through what we are calling demonstration projects. So these are small projects that are designed to last for about a year in duration. They're funded at a level of $300K by the Advanced Manufacturing Office, and that is to fund the expertise at the DOE National Lab, plus the compute resources that are needed to complete the project. What's required of the industrial partner is that they put in a 20% cost share. It's either in kind, in fact, it's typically in kind, their effort, their time, their energy, or it can be a cash contribution. And the idea is to really show what high-performance computing can do in the context of their most challenging problems. If that is successful, then we would like to start to fund follow-on projects. So these are the capability projects that might take that demonstration that was done and really take it to the next level. What's needed to make this a productized tool that can be used in the context of the industrial setting? There are lots of different execution mechanisms that we use. For the demonstration projects, to streamline the process, we focus on using the DOE short-form CRADA, which does allow for some IP protection, but we really do encourage that the results be made broadly useful and impactful to the entire industrial sector. For the larger projects, the capability projects, those can be multiple years, they can be larger in size and in duration. And then finally, we're looking at building the manufacturing community. So there was a lot of discussion, I think Bill had in his talk, about best practices, going out, advertising the program. So we've been doing a lot of community outreach where the industrial partners tend to promote and go to their conferences. For example, I'm going to FabTech in November. We had an industry engagement day earlier this year where we invited the industrial companies to come in and learn more about the program and the different kinds of projects that they can engage in. And we had about 100 people attend that meeting, and it was a very successful outreach and engagement type of meeting. We're also working very hard to grow the number of folks who can be in the manufacturing sector who have this high-performance computing expertise. So we focused a lot on our student internship programs. It's a separate part of the program where we fund on the order of 10 and maybe even as many 20 student interns every year to work on these projects with our industrial partners. So we're trying to ensure the project's success. Now, one of the main difficulties that I mentioned earlier is that the DOE lab system is hard to navigate. So the way our process works is we announce a solicitation on FidBizOps. We have 2 solicitations a year where we're asking companies to please write a 2-page white paper that tells us about their most challenging problems, and if they could use high-performance computing to solve that challenge, what would the impact be? So they do not need to identify a priori what national lab they want to work with, what codes they want to work with. They just have to tell us about their problem, and they have to tell us a little bit about how they think high-performance computing can solve that problem, and then, again, what the impact would be. We have a technical review team that gets together to review those concept papers, and we, as part of that process, will match the company with the right expert at the DOE National Laboratory. And so we think that's a little bit of a unique aspect to our program in that we try and find that right, we play matchmaker essentially, and try and find that right partnership to try to ensure the project's success. So the PI is then engaged with the company at the proposal writing stage. So we'll send back the concept paper, we'll give them feedback on the results and say, and your partner at the National Lab is X, and they will reach out to them and write the full proposal. And this is how we try to ensure that the technical scope is feasible, that the right technologies are being used to solve that industry challenge. And so, should the full proposal be awarded, then there's basically a 2 to 4 month process where they go into the negotiation for the CRADA. We talked about the different mechanisms for funding industrial partnerships, and yes, they can take some time. So the current status is that this particular program was started in 2015, so it's been going for about 2 years now. The AMO initially heard about what we had done with the HPC for Energy program at Livermore and said, that's a really good idea, I'd like to try that out. And so they started by funding 5 seedling projects and engaged with us to build a governance model and a process for how we would do industry outreach, for how we would manage the process across the DOE National Lab complex. It's not just a Livermore program. And then how we would then manage the results that we get back from industry. So in 2015, in the fall of 2015, we had our first solicitation. Lawrence Berkeley National Lab and Oak Ridge National Lab joined us as partner laboratories in running the solicitation and running the program. It was a $3 million solicitation at the time and funded 10 demonstration projects across, again, the national labs. At that time, it was just Berkeley, Oak Ridge, and Livermore were the labs that basically got the process started. And we used a lot of this, the seedling projects and the inaugural solicitation to kind of iron out a lot of the challenges that you might face working with industry and running a program like this from the national lab space. Now we're in, I would say, steady state, and we're growing to some extent. We've had 3 solicitations since then. We've just closed our 4th solicitation. Every solicitation, we have it twice a year, typically in the spring and in the fall, although with the administration change this year, things were delayed a bit, so we might be moving to summer, winter as our time frame. We've added development projects, capability projects, and I'll talk a little bit about one of those in a moment. We're now expanding it to include additional national laboratories. So in the last round, we funded projects that had partnerships at Argonne, NREL, and NETL, in addition to those at Livermore, Oak Ridge, and Berkeley. And in the last one, the last solicitation, there was a new focus area that in addition to the clean energy technologies and reducing costs in the manufacturing process, we added a materials in severe environments as a precursor to one of the ways in which this program is growing and expanding into new areas. So every solicitation, we get on the order of 40 concept papers. Our last solicitation was our highest response to date, where we got close to 60 concept papers. And so I think the word is getting out and companies are responding. So we have a very diverse portfolio. Over the last couple of years, we've funded greater than $13 million in projects. There's been over 41 projects that we have executed in terms of demonstration projects with 33 different industrial partners and 6 different national laboratories. So 40 of those were demonstration. One was a capability project with a consortium to look at the U.S. steel manufacturing area. And then we had a seedling project that's funded by the Office of Transportation. So not only is the Advanced Manufacturing Office engaged and participating in this program, other offices are very interested in this model and how they can be bringing high-performance computing to the companies that they are growing and developing. So you can see, you know, our array of company logos. The companies themselves range from very small startup type companies that are focused on brand new technologies, new clean energy technologies. They have maybe a handful of employees, one of whom may do some modeling and simulation and can really use HPC expertise, to consortia where companies get together or are led in a consortia from a university to look at some challenge that's facing the entire industrial sector, to very large companies that are using high-performance computing but need the expertise at the DOE national labs to take that next step. So the last solicitation that just closed for the concept papers, we again have about $3 million available. The new area in materials in severe environments was mentioned. Of the 57 concept papers that we received, about half of those are going forward to the full proposal stage. And we are increasingly seeing new ideas for follow-on projects. So the first initial round of demonstration projects have completed. And of the 57 concept papers, we had, in this case, 5 that were follow-on projects that are looking at how can we the company, take that next step with the national lab partner. So just to give you some demographics of the concept papers, it's been very, very diverse in terms of both the geographic distribution of the companies, where they're coming from. You can see we've got a very large collection of companies that are in, you said there's a laser pointer. Oh, yep. In the Northeast, in the manufacturing sector, but there's also some on the West Coast, in the Bay Area, and down in near LA and San Diego. An area of growth, we think, is probably in the Gulf, where there's lots of chemical companies and chemical processing plants. And so we really want to expand and grow into that area, and that'll be a focus of outreach for us going forward. In terms of the proposal submissions, in terms of the industrial sector, you know, you can see underneath there's a lot of different industrial sectors that have applied to the program. But a lot of our focus comes from things like aerospace, automotive, clean energy, machining, casting. In terms of processes that are being used, additive manufacturing right now is very, very big. Trying to understand that process, what are the results of the metals that you get out, the parts that you get out, how strong are they? Are there ways to make them more consistent, et cetera? There's lots and lots of work trying to understand additive manufacturing. But casting, semiconductor fabrication, lots of different processes that we're seeing. And then in terms of the disciplines, there was a comment on, again, I think it was Bill's slides this morning, about how expertise at the national labs that are used to develop basic science capabilities can be transferred into industry. We see that in spades in this program. So the kinds of things that they're looking for are things like computational fluid dynamics expertise, or materials modeling through molecular dynamics, very large-scale simulations that take advantage of things that can be used both in basic science, through the engineering applications that we have at the DOE lab, and into the industrial manufacturing sector. So with most of the time I have left, I'm just going to go through a few key examples to highlight the kinds of projects that we're funding through this program. Again, we're going to hear in depth in the last session today from 2 different projects. One is from Procter & Gamble that focuses on fiber simulation, think paper towels and toilet paper kinds of things. And then the other is with Shiloh, which is looking at casting. And there we have both the national lab representative and the industrial representative to talk about different aspects of that project. So when I look at the kinds of things HPC for manufacturing is doing from the perspective of extending our knowledge, there are a couple of different ways that I broke that down into a taxonomy. And so the first is really looking at scientific knowledge and looking at that across industrial sectors. So I think a prime example of that is in the creation of new lightweight alloys. So there is a consortium called LIFT, which is looking at lightweighting of alloys in the manufacturing process. We have a collaboration with UTRC and University of Michigan, which is the lead for the consortium, that's looking at aluminum alloys, aluminum lithium alloys for turbines in airplane turbines. So if you can move away from titanium, you can get maybe a reduction in weight, and I forget the percentage offhand, a few tens of percent reduction in weight, which can save you on the order of $13 million, 13 million gallons of fuel and $26 million in savings across the industrial sector. But what they don't know is how strong those alloys are going to be, particularly in the high stress environment of firing up a turbine, takeoff, landing. Those kind of environments are very, very stressful for the alloys. And so they are doping them with various amounts of lithium. And they want to understand how does that impact the strength. So we've been using high performance computing to look at different alloys, different amounts of lithium, different processes for incorporating that lithium into the aluminum lithium alloys, and looking at the density of the dope, and then predicting the yield strength for those different alloys, taking that back to the industrial consortium so that they can then build a model that they can then use in their advanced modeling of the turbine blades. In additive manufacturing, one of the things that happens in the metal cooling process is you'll get this dendritic growth, and that can significantly impact the material properties of the final metal that's resulting. And so they're trying to really understand what does that dendritic growth look like, both at kind of a more of a macro scale, but then also at a very fine scale. And so we've been looking at a couple of different binary and ternary alloy type systems that are nickel based, and looking at the dendritic growth process using different phase field models. And this is with Oak Ridge and Livermore with UTRC, and they're trying to predict crystal growth over very large domains with, again, these phase field modeling to look at, how do these dendrites impact the material properties of the system. Another way in which HPC for manufacturing is widely used in the industry is looking at the workflow and improving the workflow. So the paper towel design you're going to hear about later from Will, so I'm not going to talk about that one, but I'll say a few words about the weld prediction tool. So this is with the Edison Welding Institute, which is at Ohio State Supercomputing Center, and it's with Oak Ridge National Lab. And they're trying to build basically that next generation of welding simulation software that small businesses and companies can then use to predict what's the performance of my weld going to be, or my joining technology. And so the current technologies were relatively slow. They ran on desktops. So the question was, can we use high performance computing to both improve the modeling and simulation capabilities behind the physical processes associated with welding? So for example, the thermal analysis or the microstructural analysis, but also make it much, much faster so you get quicker turnaround time. And so this is a project that's ongoing. They are developing those new models now in conjunction with EWI and moving that forward. In terms of improving operation in energy-intensive environments, there's a couple of examples here. One is in glass making. So in this particular case, there are furnaces that are used to create the molten glass. Those furnaces can get a lot of buildup, or the operating parameters cannot are not idealized. And so the idea is to use high-performance computing to run very high-fidelity models that are fully validated. From those high-fidelity models, create reduced order models that can be run very, very fast. So for example, in an operational setting, the glass furnace operator can adjust the parameters of the glass furnace by using these high-order model, or these reduced order models, to save production time every year on each furnace, and to avoid carbon dioxide emissions, basically to optimize the process of that furnace operation. And then similarly, if you look at the manufacturing of steel, again, there's lots of ways. If you start a steel blast furnace up, and I'm not a first-hand experience of this, but apparently they'll run for a good 10 years, and they'll shut down only every so often for things like maintenance. So the question is, how can they optimize the blast furnace production? Maybe reduce the amount of coal coke that's being input into the system, maybe change the oxygen enrichment parameters or other kinds of parameters in the operation to look at that. That was well beyond the steel manufacturing's capabilities when we started this project. They had a small code that was in collaboration with Purdue National Lab. It's a consortium. And so they wanted to use high-performance computing to increase the speed of that code, to parallelize it. And now they've got a code that's 100 times faster than the old codes were. And then to also run very large-scale parameter studies using that improved code to look at, for example, like I said, the coal coke usage as a function of, say, oxygen enrichment. And then looking at new products and processes, new clean energy technologies. So we're looking at, for example, things like LED light bulbs. So there's gallium nitride crystals that could be used to significantly improve the energy costs for LED lighting, reduce it by 20%. And the problem with these gallium nitride crystals is they're grown in these monothermal reactors, and it's not really very well understood. The processes inside the reactors are very complex. The fluid flows are very complex. They were getting very non-uniform crystal growth inside the reactors, and so that was causing them to have very low production, and so it wasn't economically feasible to use these gallium nitride crystals because of those variabilities in the manufacturing process of the crystals. So we're using high-performance computing to model the inside of that monothermal reactor. So looking at the CFD flow, looking at where the chemical reactants are going, showed that there's a much more complicated flow structure than they had originally thought, in their thinking through it. The CFD showed that they were able to improve the predictions of what the temperatures were going to be. They were able to change some of the parameters so they had a more uniform temperature distribution throughout the reactor and get much more uniform growth of the crystals. At least that's what they're projecting they'll be able to do now that they've got insight into what's going on inside the reactor. And then similarly in paper making, which before I started this, who knew? Paper making is the third most energy intensive industry in the US, because it turns out drying paper is really, really heat intensive, and there's a lot of paper that we dry. So the idea here is in the paper making process, it goes through these rollers, and there's a felt liner on the rollers that presses the water out. And the question is, can they optimize that process so there's a minimum amount of water that's reintroduced into the paper as it's leaving that roller? It was getting re-wet. They call it re-wetted. And so if they can minimize that re-wetting process, they can then reduce the amount of drying time and save something on the order of 80 trillion BTUs in energy consumption a year by optimizing the paper drying process. So those are the various examples of the kinds of things we're doing with the HPC for Manufacturing program. If it's successful, if our program is successful, we will accelerate development and deployment of these energy efficient manufacturing and the production and adoption of clean energy technologies. So these are things we're striving to do with the demonstration projects. In addition, one of the metrics for our program is that high-performance computing becomes useful to a wide array of industrial users, not just the big companies like GE Global Research and UTRC, which, again, have very sophisticated modeling and simulation capabilities now, but also the small companies like Sora and Vitro Glass and other companies that are smaller. We want to encourage and build more collaboration between the DOE labs and the US manufacturers to reduce that barrier for navigating, how do I find out what's available to me at the DOE national laboratories? And then on the flip side, improve the capabilities at the DOE national labs. And Will, I'm going to ask you to talk a little bit about your experiences with that from the perspective of the Procter & Gamble project. So we're growing overall as an idea. So there's a HPC for Energy innovation umbrella that is starting to really take off. I would say, right now we've got HPC for Manufacturing, which is a well-established program, which is growing in and of itself. But right now, there's a new program, HPC for Materials, that is getting ready to be launched, funded by the Fossil Energy Program. They want to do a small set of seed projects. They've committed some funding to this. A notice of intent is about to go out for a request for, interest and information. There'll be a workshop in October. They're hoping to have their first solicitation in the January timeframe, and it'll be run using a very similar process to what we've been using for the HPC for Manufacturing program. And so with that, I will close since my infinite time ran out, and I'll be happy to take any questions. So, yes.
The aspiration.
Is this on?
It is, yes.
Okay. We've been talking about SMEs, adopting HPC for a decade, more, 15 years, 20 years I've been involved in this, right?
Right.
And it's very aspirational. We keep talking about it, but we still haven't kind of flipped the switch because it's hard and to kind of build through their workflows. So I want to understand, what's the intention here? How do you have an operational model on how you might do that? What does it look like?
Yeah, so I think the main thing is coming back to the follow-on proposal work for the companies where the demonstrations are successful. So I think I can talk about this, is the glass furnace operation that I talked about. We demonstrated that you can build a reduced order model and that it can be very quick in, looking at different parameters and optimizations for the furnace operation for the glass furnace. But it's not yet been productized. It's not really used in production yet. So they have submitted a follow-on proposal to do exactly that, to look at a couple of different furnace models, to get that incorporated into their workflow so that it's on the plant floor. And then using that in their everyday use. That's a little bit different, right? Because we've taken high performance computing and we've created a reduced order model that can be then used on the plant floor. So that's a little bit different, but that's something that we're looking at. I think, places like US Steel are really interested in the parameter studies that we've been doing. And again, it's how can they take high performance computing and answer a question that will then help them in their businesses? The main thing that we've been seeing in terms of making it operational for companies going forward. Yes.
Having been in this for so long, kind of trying to cram it down into a workflow as opposed to how do we insinuate ourselves bottom up to a business model workflow. Many of these companies don't have any of the skills to actually really leverage and use
right.
these technologies. But some of the successes just to consider is when a large scale vendor propagates the capacity.
Right.
Accountability for that end-to-end. It becomes participating in the supply chain. You actually have to participate in the utilization of these models and so on. So maybe you want to do a bunch of experiments with different business models and see which ones stick where.
Yeah, so we can talk about that. Susie and I were brainstormed several months ago about supply chain and what does that mean. I remember that phone call. So yes, I'd love to talk about that more offline based on your experience.
Just a quick question. I noticed that you're in a wonderful position of being oversubscribed. You have more applications than you can provide. Can you say anything about the people you rejected, why they were rejected, and do you work with them to kind of say, okay,
yes.
Here's if you had done this, we would have moved you to the front of the list?
Yes. So for example, in the last solicitation, we only put forward maybe 50% of the proposals concept papers that we get for full funding, because we don't want people to go to a lot of effort when there's only $10 million available. I'm sorry, $3 million available for 10 projects. So the ones that tend to go forward tend to be high impact. They have lots of broad energy impact, or they're developing a new clean energy technology that will have lots of impact. They're able to articulate why high performance computing in particular can help them solve that problem, as opposed to just being part of the process, but why high performance computing is relevant and necessary. In general, I will say, well, we don't require that they identify the lab and the codes up front. And we have put forward, so for example, in the 20 or so that went forward this time, 6 or 7 of them, or maybe even 8, had not identified a lab. But they had been able to articulate how high performance computing was going to be needed, and a little bit about what their technical plan was going to be, so that we could see, yes, that looks feasible. And that's something that the labs can help with. So the ones that don't go forward tend to either not be appropriate for the program, i.e. they're not really in the manufacturing sector or the clean energy sector, or they have not really articulated a technical plan that's HPC relevant. We don't see how it's a high performance computing problem, or it's just not feasible. And so we provide feedback on each and every concept paper. We have a short little review that we provide that says, we can work with you to help you improve this. We encourage you to talk to your industrial, or to the lab experts ahead of time in preparation for the next solicitation. So we do get a couple concept papers that go through the solicitation process once or twice, twice or even 3 times before they are really at that mark that they can move forward. So yes, we do work with the companies.